In this example, we're going to see how to create an unordered list, and the unordered list will extend the list ADT that we've seen before, and it'll add methods add to front, add to rear, and add after. So our first implementation will be an array unordered list, which uses an array list as that underlying data structure. Again, using inheritance to get the array list, although we could use containment where an array list was a data member of our array unordered list class. And that would be an interesting change for you to try to make on your own, just to see that you're able to see what the difference is. However, it's not a whole lot of difference in the code. It's really just how you use the array list methods. And then we're going to implement that unordered list abstract data type interface that we just saw. So since we have an array, since the array unordered list is an array list, we can just call it super methods, and these are similar to what we have in the array list. We have a default capacity in the default constructor, or we can pass a capacity and it gets set to that size. So we have a couple different possibilities. We can add to the front, in which case, first off, if the size of the array list that we're using isn't big enough, we expand its capacity, and then we move everything in the list up 1 because we need to put the new element we're adding at index 0 since that's the front. So we shift everything, and that's what this loop does. We start at the rear, and we go down to index 1, and we say that whatever is in that index we're looking at, copy the previous index over 1, and that does the shift. So now we set list 0 equal to the element we're adding. We increment 1 to rear because if you remember in the array list, the rear variable keeps track of the next available index in the array list, and then we increment mod count because we've made a change. And that's what again, that mod count is what we use to ensure that any iterator we generate off of this becomes invalidated once the array list changes. Adding to the rear is actually a little simpler because we don't have to shift anything. We just put the element in at the rear index, and then increment rear, increment mod count. Now add after is a little bit more complicated. We take the element we're going to add as a parameter, but we also say add it after the index where this is stored. So the first thing we do is we look for what we're going to add it after. And if scan actually reaches the rear index, remember there's nothing stored at the rear index. So that means it's not there. And so we'll throw the element not found exception, which as a reminder is just an exception that we wrote. We extend runtime exception, and we use the runtime exception constructor, except we pass the message that the target element is not in this collection. And collection is the string that we passed here. Keep in mind that scan has the index where the target was found. So we're going to increment this, and that's actually going to now be the index where target will move. We're going to shift all the elements over by 1, starting at the rear and working our way toward that scan index. Then scan is the index where we're going to insert the element. And remember, it's 1 after the target element's index. And once we've done that, we've added the element. So we increment rear to indicate that there's now that open spot is now moved over 1 because we've inserted 1 element, and we update the mod count. Now the linked unordered list is not implemented, and that's left to you as an exercise to try. Again, the logic is all going to be the same, except working with links versus arrays is slightly different. Adding to the front is actually a little simpler because you just need to add to the front. You don't actually have to do the shift with add to front or add after. So that's one thing that makes this a little more convenient using a linked data structure. Add to rear, if you don't have a rear reference, can actually be a little more complicated because you do have to iterate through the array. Okay, so let's see how we would work with one of these. So this is our driver we used with our ordered list. So let's add an unordered list so that we can see the difference. So we'll make a new array unordered list of integers. And again, we'll set the initial size to 2. And then here we'll just add that same number to the unordered list. So we actually have 2 different versions. So we'll say array unordered list add to front. In fact, let's do another array. Let's do 2 of these. So we'll do array unordered list 1 and then 2. We'll add to the front of one, and then we'll add to the rear of the other. Okay, so let's see. Let's say UnorderedList 1 and 2. And actually, let's do this. I'm going to put their size. I'll put the size out too. And that way we can just see how those sizes get updated. So let's see. I guess I should try to make sure my syntax is correct here. I think that's correct. So let's run this. Oops. We added too many here. And we don't want to add II. We want to add num. Okay, so 2 little bugs. Okay, so let's run this and see what happens. Okay, there we go. Now you'll notice UnorderedList 1 we add to the front. So our numbers were 12, 94, 62, and so on. And you'll notice when we add it to the rear, we get those numbers reversed. And then our ordered list, again, same set of numbers, but in this case they're sorted because each time we added the number in its correct place in order in the list. The reason we use the interface here as the object reference type is because if you went back and implemented the linked unordered and linked ordered list classes, you could actually just change this to a linked ordered list, this to a linked unordered list, and your code would work exactly the same. By using the interface there, we don't have to worry about that implementation type, and we can change it to pick an implementation that suits our needs better, whether it's performance or whatever.